Welcome to the UASMaster video tutorial. In this video tutorial we want to talk about setting up the project for the demo data. In this video we are using version 8.1.0. Therefore, if you are using an older version, the graphical user interface can be different in your place. To follow up this video, you need to download the demo data, which was shown in a previous video. Extract the executable, and you will have 3 folders, which we will use here as our demo data. In case you already have done a project in a previous version, you can run the open function to load an older project version, and it will be converted to the new one. For our video here, we will create a new project and start the new project by hitting the button UAS. 2 windows will open up: the UAS project editor and also by default the first time the basics window, which is the window which will open up when you go to project editor and select the first entry, basics. The basics window we will use to set up the target coordinate system. So everything we will run in this project will end up in this coordinate system. For our demo data, we have the UTM-31 North project system, which you can either find here by selecting from the project system tab and scroll down to WGS84 and select here the UTM zone 31 North, or you can also type in directly the EPSG code here on the right side and select 32631 and find, and it would jump here to this location. We select it as our target coordinate system. After defining the target coordinate system, I can close the basics window and we continue with the next entry, which will be the camera for our project. In the camera dialog, we can create here a new camera by hitting the plus button, where the dialog opens up to select the sensor type, which is for UAV systems only CCD frames supported. We offer a setup of templates, and for our case we will use the Trimble UX5. In case you have a sensor not supported from our template, you can use custom, and then you would need to define the entries yourself for most parts of it. Selecting the template offers us already the sensor size and approximate values for focal length and distortion values. For the demo, I call my camera here demo data and add the camera to our dialog. You can expand here this entry where you have values for the platform, which is the camera mount, which is already by default set up correctly for the templates here. The calibration, where we have a focal length, a pixel size, and the coordinate system of the sensor itself, which is already also defined with good starting values for the UX5. Therefore, we will keep these values as they are entered here. In case you have your custom camera, you would need to know these informations. You would need to know the focal length, you would need to know the coordinate system of your sensor, you would need to have the pixel size, and enter them then manually into it. We don't have offsets for this data, and here predefined distortion values are existing from a previous project. In case you don't have any informations, you leave them all at 0, which then will be calibrated during our project setup. In our commentary here, you could enter if you have investigated some problems with the camera. That's it, so we can say OK, and then we have the camera defined. In the next step, we will import our imagery. So we select the frame photos and we import the files. All my data is in one folder, so I can directly import a complete directory. If your data is split up on several subdirectories, you could also add subdirectories or individual files. I will go to our demo data and select the images folder. This is a folder selection, so if you scroll through, you don't see any images here, but in this folder our JPEG imagery is existing, and therefore I can select it and we see here our JPEG images appearing. Our data is around 90 meters on the terrain. This is not the flying height, this is the terrain height, where the images are on the ground approximately. At this moment we don't have gnss IMU, so we will not initialize with it. We go to the next and we will define an image ID. The image ID later on needs to be brought into association with the gnss ID. They need to be identical. The same, therefore here we will only use the digits, and I will skip deleting zeros, and then this value here I will then match with the gnss ID. After importing the images, we can see now the file locations and that the images are online. At the moment we don't have orientation data for it, which we will import through the gnss import. So please don't use here this orientation import, which has a different meaning, but we will go to the import of gnss IMU and select now here the file which includes our gnss information. This can be found in the input folder, where we have an Excel file which is in geographic coordinate systems, latitude, longitude. So we will start here from line 2, and we also have this file prepared with some group separators, so the strips will be automatically generated here already. You don't need to do this, you can also start the strip generation later on, which is an automatic process, but here this makes it just simpler and easier to get good strip definitions. We have here commas that separate our columns, so I will use the commata, and we can then have here the separation of the input data. And now we need to associate, so this here is our ID, this here is latitude, so be careful to not select here longitude. This one here is longitude, this here is the height, and also the orientation here is yaw, pitch, roll. So you have to say the first here is yaw, the second one is pitch, and the third one is roll. To make our gnss ID identical as the image ID, we will again here only use the digits, and we will skip deleting zeros. And now the ID is identical as our image ID, and therefore this should then fit and make it easy to associate it. Very important here, this is now our source coordinate system. So where is the gnss data coming from, not where it will end up. So therefore in our case we have to change this, as the data is a geographic system coordinate system and it's a WGS84. So this is now different, of course, than our target system. The angular units are degrees, which is fine, and also the rotation sequence is not a photometric, but in our case an aeronautical, roll, pitch, yaw, and the other things we can stick as default, so we don't have any compensations or lever arms to be applied. In this import we can also initialize our photos. So therefore you remember in our photo window the orientation was 0, 0, 0 everywhere, and now we can apply the gnss information to our photos with this check mark, and as I mentioned we can now generate the strips here from the given informations. So we have automatically generated now these 6 strips, and we can finish the import, showing us now our gnss data here in the window. We need to define standard deviations, how accurate the gnss data is. In our case we have not post-processed GNSS. This is GNSS data which is about 6 to 10 meter accurate only, and the IMU data is not well defined, so I will just stick with the default settings here. Then we can say OK, and when we go back to the images, we see now that we have for each photo orientation data, and this is because the ID of the image and the ID of the GNSS was fitting, and therefore the orientations were able to be applied to the photos. Finally, we import our control points. Also, we go here to our input folder from the demo data and select the GCP file. In this case, we see the GCP file is already in the correct projection. So the source where the data comes from is identical to the target, so we can just keep it in the same system. We will start the import from row number 7, and here again we need to define the separation. In our case, the tab and blank is sufficient, and we can say this is our ID, this is X, this is Y, this is Z, and we keep the IDs as they are, which are fine for us. The source, as I mentioned, is the same as the target, so we can stay with WGS84 UTM zone 31 north, and therefore our control points have been imported. For the control points also we need to define standard deviations. We can use here an automatic tool where we stick with the default settings, where it's mentioning that the standard deviation is smaller than 2 microns. 2 microns is a value very often used where the accuracy is not sure to be achieved, but for our case we say yes, we don't want to go to 2 microns, we want to stay with the 0.5, and here also I keep the standard settings for the automatic points. The real-world accuracy, we also stick with the default settings here of around 1 centimeter accuracy, and the height also around 1 centimeter. That's it. This is fine. We have now imported all the data. We can now save the project. And close the project editor, and you should then see in the UASMaster a 3D view opening up. We have here 2 more control points in the lower left which are not related to our project. In case you don't want to use them, you could also go back to the project editor and remove these 2 control points, and then these 2 control points here, when you remove them and save the project, then it will zoom more to the center. This is up to you. The 3D view allows us also to use here some navigation on the data. So if you select one of the 3 axes of the globe and you keep the right mouse button pressed, you can rotate the view around these axes. So I can either select here around the X, Y or Z and take a look here at the data and evaluate if perhaps the orientations make sense or not. In case you want to go back to default, you can just make fit view and then continue your processing. This is the old main view, which you know from the previous versions, and I hope therefore this allows you now to continue with the processing of the data from the demo data. And so I hope we see each other in the next video. Have fun and enjoy the videos. Bye!